Problem 2 asks about the convergence or divergence of certain series and also whether they're absolutely convergent. The first problem is a series over 1 over n cubed plus 3. If it was just 1 over n cubed, it would be a pure p-series and we would know what to do. Well, however, it's not far away from a p-series, right? Because if n is greater or equal than 1, then n cubed plus n is certainly greater or equal than n cubed. Therefore 1 over n cubed plus n is smaller or equal than 1 over n cubed. Therefore we can do a comparison test. We note that the sum n goes from 1 to infinity over 1 over n cubed converges, because it is a p-series for p equals 3. And we notice that this is greater or equal than the sum n goes from 1 to infinity over 1 over n cubed plus n. This is just because of what we've just shown. Therefore, this also converges. Because all terms are non-negative, we get automatically that it's actually absolute convergent without having to do anything extra. In part B, we have a series over minus 1 to the n sine n divided by n squared. If we look at this series a priori, it might look rather complicated. It is actually not completely trivial to show that sine n over n square becomes strictly smaller every time. However, we will show that it's absolutely convergent, which actually will make this very easily. So let's look at the sum over the absolute values. If we do this, and we take the absolute values here, we can take, of course, the absolute values for every part of the product separately. The absolute value of minus 1 to the n is simply 1, so this will just vanish. We get the absolute value of the sine of n, and we divide by, well, technically the absolute value of n squared, but that's the same as n squared. Now we can easily see that the absolute value of sine of n is bounded by 1, so this is bounded by the sum n goes from 1 to infinity, 1 over n squared. And again, this is a p-series. For p equals 2, this is convergent. Therefore, we can conclude that the sum over the absolute values converges, and therefore the original series not just converges, but is absolutely convergent. In part C, we have a series over minus 1 to the n plus 1, 1 over square root of n. Using the alternating series test, we see immediately that this series is convergent. Why is this the case? Because 1 over square root of n, the absolute part of each term, is greater or equal than 1 over the square root of n plus 1. And because we have this factor 1 over 1 to the n plus 1, the sign changes every time. So it is convergent. However, it is not absolutely convergent, because if we look at the absolute values, if we look at the series over the absolute values, 1 over square root of n, that is nothing else but the series sum over 1 over square root of n, which is a p-series for p equals 1/2. and 1/2 is strictly smaller than 1. So we know it diverges. Therefore, the original series is only conditionally convergent. Part D, we have the sum over n squared over 2 to the n. One could do this, for example, with a limit comparison test. That's how the solution on how the posted solution does it. But it turns out that we can also simply do a ratio test. So let's do a ratio test for this series. What is the absolute value of the quotient of the n plus first term divided by the nth term? Well, this is the absolute value of n plus 1 squared divided by 2 to the n plus 1, and the whole thing divided by n squared divided by 2 to the n. Once we start simplifying this fraction, we see that almost all of the 2 cancels away. So we get n plus 1 squared divided by n squared times 1/2. Actually, these are all positive terms, so we can just forget about the absolute values. So this is n plus 1 squared divided by n squared times 1/2. What happens if we look at the limit if n goes to infinity? Well, n plus 1 squared over n squared goes to 1, so this whole thing goes to 1/2, which is smaller than 1. So by the ratio test, the series is convergent. And furthermore, since all the terms are non-negative, it is actually absolute convergent.